Today we're going to take a look at how we create prototypes. So first, these are the things we're going to look at. What is a prototype? Prototyping by hand, 3D model to a prototype, and then some different kinds here. Rapid prototyping, stereolithography, selective laser sintering, fused deposition, laminated object manufacturing, and then just another type of 3D printing. So we'll take a look at each of these. Now you're going to want to add some of this to the notes document that I explained in the instructions. So feel free to pause this along the way if you need to. First of all, the definition: a prototype is an original full-scale and usually working model of a new product or new version of an existing product. So if you're trying to make a impeller blade or a fan blade, to prototype, it means you're actually making something that is going to work. Prototyping by hand although prototypes have always been a useful aid in the design process, creation of prototypes has evolved from handmade to machine-made. Remember back in our history, everything was done by hand, by artisans, and now with machines we can prototype things a lot more quickly. So here's how we do it. We go from a 3D model to a prototype, and so you're modeling something on maybe Inventor or SolidWorks, and then we print it, and usually you have to save it as an STL file before you do that. The first type of rapid prototype, or actually just to explain this to begin with, rapid prototyping creates a three-dimensional solid object directly from a computer-generated model, and it utilizes product areas of design, verification, and testing. So this is an example of a rapid prototyping machine. And software will take the model and slice it into thin sections. So right over here you can see there's a bunch of different 3D printed objects, and this looks like this is in kind of like an area where they're cleaning them off or brushing them off. It's similar to a CT scan of the brain, a CAT scan they call them, where it just takes very thin sections and will allow the software to know how much material to lay down. The software creates one slice at a time. It's kind of like stacking a deck of playing cards. So the first example is stereolithography, and stereolithography uses a low-power laser beam that's traced across a vat of liquid polymer. So those are kind of the main things that you probably want to note, that it uses a laser over a liquid polymer. Then UV light solidifies the polymer, so solidified by UV light. The first layer is lowered, so this vat down here drops down a little bit further, and then the light comes and solidifies some more polymer. It drops further, and so on and so on. That model process is completed, and then it's cured in an oven. So here's an example of how that works.
Stereolithography, first of the rapid prototyping technologies, is a liquid-based process for making models. The models are built in layers within a reservoir of a liquid, thermosetting, epoxy-based photosensitive polymer by selective curing with the ultraviolet light from a focused low-power laser beam. The laser beam continuously traces and selectively hardens the thin layer of polymer according to the CAD file. Once tracing of the layer is complete, the platform that the model is built on moves down precisely one layer. Liquid resin is then dispensed over the model, and tracing of the next layer begins. Minimum layer or slice thickness ranges from 1/1000th of an inch to 12/1000ths of an inch. Supporting ribs for overhangs and undercuts are built up along with the model and later removed by secondary operations. When the model is complete, the platform rises out of the polymer reservoir. Once the excess polymer drains away, the model is removed for post-processing, such as removal of supports, additional curing, and surface finishing. Stereolithography machines can produce models as large as 40 by 32 by 23 inches. Additionally, multiple smaller models or model components can be nested together for simultaneous building. Models made by stereolithography can be extremely precise, with thin and sharp features and smooth finishes. Substantial post-processing may be required, however, to separate the model from its supports. Additionally, polymer cost is high.
Then we move to selective laser sintering. So this is a CO2 laser that traces the shapes of individual slices across a layer of heat fusible powder. So we're using a laser and it's going over powder this time instead of a liquid polymer. So that's selective laser sintering. Make sure you note how that works. Again, a laser over a powder. And again, this just continues to lower down, and more powder is added, and then you have a leveling roller that kind of comes over and makes sure that it's all uniform thickness. So here's an example video of how that works.
Selective laser sintering is somewhat similar to stereolithography, except that the materials used to form models are in powder form, and the laser is a more powerful carbon dioxide unit. A layer of powder is deposited over the machine build area and spread evenly by a roller. Powder layer thickness ranges from 0.003 of an inch to 0.012 of an inch. The laser beam scans the model design according to the CAD file and selectively sinters or fuses the powder particles together. The model platform lowers incrementally as each successive layer of powder is similarly fused. Once complete, the model or models are moved from the machine in a cake of unsintered powder. They are then manually removed from the powder cake and finished using secondary operations. Typically, the excess powder is recycled for reuse. The principal advantage of the selective laser sintering process is the wide range of materials from which models can be created. Among the assortment of suitable materials are polycarbonate, acrylic styrene, nylon, thermoplastic elastomer, investment casting wax, silica, and zirconium silicate foundry sands, and even polymer-coated carbon steel. However, maintenance and operating costs are high. Selective laser sintering machines can produce model designs as large as 14.5 by 12.5 by 17.5 inches.
Fused deposition modeling is what we have, and this is the 3D printer that is the MakerBot replicator. This example has two spools. It has a build material spool and a support material spool, and these are fed up through this extruder. So it's using the solid plastic material, and ours is called PLA. There's other machines that use ABS, and ABS plastic is like what PVC pipes are made out of, your plumbing waste pipes. PLA is a different kind of material. It's a plant-based material, and so that's what we use. We only have a single extruder head. We do not have the option to have the support material. That light blue material can be washed away or dissolved away so that you don't have to build supports in. It kind of just makes it all solid, and then it washes away to make a lot cleaner looking part. They do sell MakerBots that offer that now, but they're a little expensive. So here's an example of fused deposition modeling.
Fused deposition modeling involves feeding a thermoplastic filament into a heated extrusion head that moves in the X and Y axes. The heated extrusion head melts and deposits the thermoplastic material on a table that moves in the Z axis, building the model. The molten thermoplastic is channeled through an extrusion tip, which reduces it to a fine bead for deposition onto a substrate material. After depositing each bead, the tip flattens it in preparation for subsequent layers, and the model is built up layer by layer. Layer thickness is typically between 0.005 of an inch to 0.13 of an inch. As it is deposited, the molten thermoplastic material is just slightly above its melting point. Solidification occurs immediately after extrusion, as the material cold welds to previous layers. The most common material used for fused deposition modeling is acrylonitrobutadiene styrene, or ABS thermoplastic, in various colors. ABS provides tensile strengths of up to 5,400 pounds per square inch. Other materials used include investment casting wax, elastomer, polycarbonate, and polyphenol sulfone. Depending on the machine, maximum part size can range from 8 by 8 by 12 inches on the smallest machine to 24 by 20 by 24 inches on the largest machine. Fused deposition modeling is moderate to fast in building speed. Additionally, most systems incorporate a water-soluble support material, which aids in support removal. The strength and heat resistance of models are also advantageous, and the variety of colors available are useful in accentuating part features.
And here's another one, laminated object manufacturing. In this one, a paper is unwound from a feed roll onto the stack and first bonded to the previous layer using a heated roller. Profiles are then traced by the optics system that's mounted on the XY stage, and after cutting is complete, the excess paper is cut away and waste paper is wound up in a takeaway roll right here. So we're rolling this thing out. This laser is then kind of melting or fusing whatever the two-dimensional shape is, and it builds it up into a three-dimensional shape. So that's laminated object manufacturing, again using a laser to melt on this this material roll, supply roll sheet, and then whatever the waste material is that's collected is just wound up over here. So here are a couple other videos that show rapid prototyping. One is rapid prototyping using metal, so you can actually print with metal. And here's another one that uses ultrasonic, so uses sound to help adhere things together. And this one I believe is metal as well.
The Pro Metal System modelers are also used for creating metal models. This system involves using inkjets to apply a liquid polymeric binder onto powder media to produce models. The models are built from steel-based powder from the bottom up. Upon completion, models are sintered to remove the binder and bond the powder particles, and then infiltrated with bronze to substantially reduce or eliminate porosity. Besides the capability of making high-strength, durable models, no support structures are required. Tooling for plastic molding processes are a common application. Ultrasonic consolidation produces direct metal parts from CAD data by ultrasonically welding layers of coiled aluminum foil strips to a prepared metal substrate. As the foil strips are placed on the substrate, a tool called the sonotrode uses high-frequency vibratory energy and moderate force to disrupt the interface surfaces, inducing interatomic attraction and metallurgical bonding between the foil and the substrate surfaces. Once ultrasonically welded, the layer is then milled to the cross-sectional shape defined by the CAD data. This process of adding material to a previous layer and then removing the excess continues until the part is complete. Like other rapid prototyping processes, ultrasonic consolidation also allows for the buildup of complex geometries, overhangs, and enclosures within a part. Ultrasonic consolidation can be used to bond a variety of similar and dissimilar metals, as well as certain ceramic metal combinations.
So that wraps it up. We should have covered all of these aspects, and hopefully you got all that stuff added to your notes.